Chapter P3 is all about radicals and rational exponents. So we're going to start out by just evaluating some square roots. So, in our first one, the square root of 81 is 9. In B, the square root of 9 is 3, and since the negative sign is on the outside, we take the square root of 9 and then we leave the negative there. For C, the square root of 1 over 25, so the square root of 1 is 1, and the square root of 25 is 5, so our answer is 1/5. In D, it's important to note that the square root of the quantity 36 plus 64 does not equal the square root of 36 plus the square root of 64. In this case, we have to treat what's under the radical as if it's in parentheses. So this is really the square root of 100, which is 10. For E, now we have the square root of 36 plus 64, so we have 6 plus 8, which is 14. For example, F, negative 3 squared is 9, so when we take the square root of 9, we are still left with positive 3. In G, it's positive 3 squared, which is again the square root of 9, so our answer is also 3. Now, when we have two things that are multiplied under the radical sign, such as the square root of a times b, we can break that into the square root of a times the square root of b. This becomes important, for example, to a, when we have the square root of 75, which isn't a nice, neat number. So in this case, we can break 75 into the product of 3 and 25. 25 is a square number, so we are left with the square root of 3 times the square root of 25, and the square root of 25 is 5, and the square root of 3 I'm just going to leave as a radical. I can also do this in example 2b, where I can combine these two into a single radical to start with, so I can undo that product rule, and so I get 50x squared under our radical, and so I can break this into the square root of 2, and the square root of 25, and the square root of x squared. So the square root of 25 is 5, the square root of x squared is x, and the only thing I'm left with underneath the radical sign is 2. I can also use the quotient rule for square roots when I have a fraction inside my radical. So in this case, the square root of a over b is equal to the square root of a over the square root of b. We can see this in example 2c, in which case the square root of 25 over the square root of 16 is 5 over 4. In D, it's a little more complicated, but it's the same thing. Except now I'm going to combine these fractions before I take the square root. So I'm going to take the square root of 150 divided by 2, which is 75, and then I'm going to use my exponent rules from P2. So x cubed divided by x is just x squared, and now I'm basically taking the combination of example A, where I have the square root of 75, so 5, and the square root of 3, but I also have x squared, so I'm going to have x outside the radical. If I am adding and subtracting square roots, I can combine two or more of them as long as they have the same radicand, which is all the stuff underneath the radical sign. So those radicals are called like radicals. In example 3a, we can add them because in both of these 13 is inside. So if this was 8x plus 9x, I would have 17x, but instead of x, it is just the square root of 13. Similarly, in example 3b, we have 17x inside both radicals, and so we have 1 times the square root of 17x minus 20 times that same value, and so 1 minus 20 is negative 19, and the radical stays the same. Continuing on in example 3C, initially it doesn't look like we can combine these because the square root of 27 is not the same as the square root of 12. But we can break both of those down into different radicals. So 27 is 3 times 9, so this is 5 times the square root of 9 times the square root of 3. And then square root of 12 is the square root of 4 times the square root of 3. So now we can do a little bit of simplification. 5 times the square root of 9 is 5 times 3, which is 15 times the square root of 3. And then square root of 4 is 2 times the square root of 3. So we are left with 17 times the square root of 3. In example 3D, we have to go through a similar process. In this case, x is going to stay there, but 18 is the square root of 2 and the square root of 9, and then there's the square root of x. And then we are left with 4 and the square root of 2, the square root of 4, and the square root of x. The things that are the same on both sides are the square root of 2 and the square root of x. And those are in both terms. So now, in this first one, we were left with 6 times the square root of 9, which is 6 times 3, or 18 times the root of 2x, minus 4 times the square root of 2 is 8, 8 times the root of 2x, which gives us 18 minus 8 is 10 times the root of 2x. To rationalize the denominator is to rewrite a radical expression when there is a radical in the denominator. You know you're done when there is no radical left in the denominator. So, in example 4a, in order to simplify this, we must rationalize the denominator. Now, we can't change the value of this because it's just an expression, so we have to multiply by a special form of 1. If we want to get rid of the root of 3 in the bottom, then we multiply by the square root of 3 over the square root of 3. So, since this is now just multiplying two fractions, in the top, I am left with 5 times the square root of 3, and then the square root of 3 times the square root of 3 gives me just 3. Similarly, in 4b, we're going to do the same thing, except we have to break that denominator down a little bit along the way. So we're going to start off with the same thing, the root of 12 over the root of 12, but that's not quite the same thing. So this is 6 times the root of 12 all over the square root of 144. Well, initially, it looks like you might just be able to say that this is 6 times the root of 12 over 12. We're not done yet because the square root of 12 is not simplified all the way. That actually equals 6 times the square root of 4 times the square root of 3 over 12. And so 6 times the square root of 4 is 12. And so those cancel, and I'm actually just left with the square root of 3. The conjugate of an expression in the form of a plus the square root of b is a minus the square root of b. All of the numbers or the expressions under the radical will stay the same, except the sign, now it was a plus, becomes a minus. The alternate, where a minus would become a plus, is also true. We're going to use this in example 5 to get rid of the radical in the denominator of this fraction. We're going to start out the same way as we did in example 4, where we're going to multiply by a special form of 1, except now, because we have an addition sign in our denominator, we're going to use the conjugate instead of just the same value. So we're going to multiply by 4 minus the square root of 5 over 4 minus the square root of 5. So when I do that, the top of my fraction now becomes 8 times 4 minus the square root of 5, and I'm going to distribute that, and I get 32 minus 8 times the square root of 5, and the bottom of my fraction becomes 4 plus the square root of 5 times 4 minus the square root of 5. Now when I do that, I'm going to FOIL, first, outer, inner, last, and so my first is 16. My outer is 4 times the square root of 5. So that's a plus a negative 4 square root of 5. My inner is a positive 4 times the square root of 5. And my last is the square root of 5 times the negative square root of 5. So that is minus the square root of 25. So this still looks pretty messy, but when I simplify this, the top is just 32 minus 8 times the square root of 5. And in the bottom, this negative 4 in the square root of 5 and the positive 4 times the square root of 5 cancel out. So the bottom, I am left with 16 minus the square root of 25, but that is 16 minus 5, which equals 11, so I'm left with just 11 left in my denominator. It's still not pretty, but I no longer have a radical in the denominator. We don't always just take the square root of a number, though. Sometimes we take the nth root. So this is going to be written in the form the nth root of a, and n is called the index. So the product and quotient rule for these roots still apply. So we're going to look at some examples of how this looks. So for the cubed root of 40, so when I write this out, I'm going to actually break 40 into its prime factors. So that's 2 times 2 times 2 times 5. Now I have 2 times itself 3 times here, so that means that I can pull 2 cubed out of that. So I can pull 2 out, and I'm left with the cubed root of 5. Our next part has the fifth root of 8 times the fifth root of 8. Because my product rule still applies, I can take the fifth root of 8 times 8 is 64. And now, again, I'm going to break that into my prime factors. So that is going to be the fifth root of 2 times 2 times 2 times 2 times 2 times 2. So that is 2 times itself 6 times. Because I'm taking the fifth root, I'm going to pull 2 out 5 times. And so that's 2 to the fifth, and the fifth root of that is just 2. And then I'm left with the fifth root with the 2 still under the radical. In C, we're using the quotient rule, so I can take the cubed root of 125 over the cubed root of 27. So in this case, 125 broken down into its prime factors is 5 times 5 times 5. And 27 into its prime factors is 3 times 3 times 3. Since in the numerator, 5 appears 3 times, the cube root of this is simply 5, and in the denominator, 3 appears 3 times multiplied by itself, so the cube root of 27 is just 3, so my answer is 5/3. In our next example of this, it doesn't initially look like we can do anything since 81 and 3 are not the same radicand. But we can break that 81 down. So 81 equals 3 times 3 times 3 times 3. So the cubed root of 81 equals 3 times the cube root of 3, which we now see in that second expression. So now we can indeed combine some terms. So we are left with 3 times 3 cube root of 3 minus 4 times the cube root of 3. So we have 9 minus 4 is 5, and then the cube root of 3 stays in my answer. Next, we're going to look at rational exponents. So when we have a fraction as our exponent. So as long as the nth root of a is a real number, where n is greater than or equal to 2, and an integer, then a to the 1 over n is equal to the nth root of a. If a has a negative exponent, then what we're going to do is we're going to use our negative exponent rule to make this 1 over a to the 1 over n. So we get 1 over the nth root of a. Now we're going to use this property to simplify some expressions. So 25 to the 1/2 is the second root, or just the square root of 25, which I can simplify to be 5. 8 to the 1/3 is the third, or the cube root of 8, which is 2. Now, when we see negative signs in our expression, we're going to have to be very careful. In this case, we're going to end up with an even root, so we must have a positive number inside the radical. So what we're left with is the negative fourth root of 81. The fourth root of 81 is 3, so this equals negative 3. In example D, we have an odd root, in which case it is okay to have a negative number inside the radical. So here, we're going to have the cube root of negative 8, which equals negative 2. In E, it's a negative exponent, so we're going to use our negative exponent rule. So this is 1 over the cubed root of 27, which is 1 over 3. Next, if my number A has an exponent that is a ratio, but it does not have 1 in the numerator, as long as the nth root of A is a real number and m over n is a positive rational number, and n is greater than or equal to 2, and an integer, then a to the m over n is the same thing as saying the nth root of a raised to the mth power, but also you can write that as the nth root of a to the m. If the exponent is a negative number, then this is going to be the same as we did before. We're going to use our negative exponent property. So that's going to be 1 over a to the m over n. So that equals 1 over the nth root of a, all raised to the m. What this looks like in an example is the top of my fraction becomes my exponent, because exponents go at the top of an expression, and roots of a tree are at the bottom, so the bottom of the fraction is the root. So in this case, I have 27 and the fourth, but it is the cubed root. So in this case, the cubed root of 27 is 3 raised to the fourth power, which equals 81. In B, all right, the other way to write this is the square root of 4, all raised to the third power. So the square root of 4 is 2. 2 cubed equals 8. In C, we have a negative exponent, so this becomes 1 over 32 to the power of 2/5. And the other way we can write that then is 1 over the fifth root of 32 squared. And the fifth root of 32 happens to be 2, so this is 1 over 2 squared, which equals 1/4. Now we're going to look at simplifying our expressions using our properties of exponents from P2. So we're going to take our numbers and multiply them together. So 2 times 5 is 10. And then we're going to use our product rule, and we're going to have x to the 4/3 times x to the 8/3. Since I'm multiplying those, I add my exponents together. The 10 is going to carry down, and then I'm going to have x to the 8 plus 4/3, so that is 12/3. Now, just like any fraction, I can now simplify my exponent. So again, the 10 stays where it is, but now I have x, and the 12 divided by 3 is 4, so my answer is 10 times x to the 4th. In B, I'm going to do the same thing. I am going to take the 20 and the 5 and simplify that first. So I know I'm going to have 4 in my answer. And then I have x to the 4th, and then since I'm dividing, it's minus 3/2, and I'm now going to simplify that. The 4 is going to stay in my problem, and I have x, and 4 is the same as 8/2, minus 3 halves, so I have like denominators. And so my final answer is going to be 4, and then x to the 8 minus 3 is 5 halves, which I could also write in radical form, but in this case I'm going to leave it like that. The final thing we're going to look at is reducing the index of a radical. So that means I want to take this number here and make it smaller. So the first thing I want to do is put this into exponential form. So to do that, it's still going to be a base of x. Now remember, the exponent goes in the top, so this 3, and then the root is in the bottom of my fraction, so it is 3/6. And now I can just reduce that fraction. So 3 divided by 6 is the same as 1 divided by 2. It's 1/2. So that is x to the 1/2, which I can then put back into radical form. So this is x raised to the power of 1, and then the square root, which is my answer. Similarly, in b, I'm going to convert this into exponential form. So this is x to the 4th divided by 12 in the exponent. So 4 divided by 12 is 1/3. So that gives me the cubed root of x as my answer.